If the goal is longevity, age products may be a problem. Feeding age products to mice on a calorie-restricted diet, CR, shortens lifespan, and we can see that data here. So we're looking at cumulative survival on the y-axis, plotted against longevity or lifespan on the x. And we can see that mice that were subjected to 40% calorie-restricted had a significant extension of lifespan. Now, note that calories and age products are reduced on the calorie-restricted diet, and we can see that here. So when comparing the regular diet, reg, versus CR, we can see that food intake on the CR diet in grams per day was 3 grams per day versus 5 on the regular diet, so a 40% restriction of food intake. And that resulted in a 40% reduction in calorie intake for CR mice. But also notice for the age product CML, which stands for N6-carboxymethyl-Lysine, we can see that this age product CML was 37% less on the CR diet because they ate less food when compared with the regular diet. So is it the calories that's leading to the extension of lifespan in CR mice, or is it the age products? So to test that, the authors of this study then added age products, more specifically CML and others, into the food. So does that affect lifespan? So first, let's look at the dietary composition for mice that were fed the high age product diet as shown there. So first, we can see that food intake and calorie intake were similar, exactly similar to what CR mice ate. But we can see that age products on the CR high diet were almost 3-fold higher than mice that were on CR and also higher than on the regular diet. So what was the effect on lifespan for CR mice that ate the same amount of food as regular CR mice, but that had a higher age product level in their diet? And we can see that the lifespan extension for CR mice is gone. So feeding age products to mice, even on a CR diet, shortens lifespan. Conversely, reducing dietary age products increases lifespan, and we can see that data here. So once again, looking at cumulative survival on the y-axis plotted against lifespan or longevity in age or weeks, we can see that mice were fed a regular age product containing diet in the rectangles, and then a low age diet in the triangles. And we can see that mice that were fed the low age product diet had a significant extension of lifespan. So are dietary age products related to health or longevity in people? Because these data are in mice. We want to know if this can improve health and longevity, potentially longevity in people. So there weren't any pretty pictures to present, so we can get all the information we need from the title of this paper. Dietary intake of CML is not associated with an increased risk of mortality in this study of 29,000 people. So does that mean that dietary age products are irrelevant for human health? Now, note that this is only one study. If anyone's come across all-cause mortality data as it associates with dietary intake of age products, please leave it in the comments below, but I haven't come across that data. Only one study so far. Now, conversely, in contrast, blood levels of CML increase during aging. And we can see that here. So blood levels of CML on the y-axis plotted against age from the 35 to 85-year-old age range. And we can see that the age product CML significantly increases in blood during aging. So what's the importance of the relatively higher levels of age products that are found in blood during aging? So relatively higher blood levels of CML are associated with an increased all-cause mortality risk. So first, we're looking at data for women, and these are older adult women from 65 to older than 90 years. So we're looking at survival or all-cause mortality risk on the y-axis, and with about a 5-year follow-up on the x. So we can see that older adult women that were in the lowest 3 quartiles of CML blood levels, so less than 0.68 micrograms per milliliter, had improved survival when compared with women that had higher than greater than 0.68 micrograms per mil for CML. So relatively higher blood levels of CML in this study of older adult women were survival, increased all-cause mortality risk. So what about data for women and men, so both genders? So again, we're looking at all-cause mortality or survival on the y-axis, and in this case, in this study, the follow-up time was longer, up to about 7 years. And again, we're looking at 65 to older than 90-year-olds. So for people that were in the lowest 2 tertiles of CML in blood, so in this case, less than 0.4 micrograms per milliliter, they had improved survival, whereas the highest tertile of CML in blood, greater than 0.4 micrograms per mil, had an increased all-cause mortality risk when compared with the lower 2 tertiles of CML. So what's contributing to the higher circulating CML in older adults? Even if we discount the role of diet, what's contributing to the higher blood levels of CML in older adults? So first, note that CML is increased in the presence of high blood sugar or hyperglycemia. So in this study, they used a hyperglycemic clamp, and what that means is that they infused glucose that increased it from basal levels of 90 milligrams per deciliter up to 180 for 2 hours. So blood glucose was 180 for a 2-hour period continuously. So what was the effect on blood levels of CML? So after 2 hours, we can see that CML levels in blood were significantly increased as a result of the glucose infusion up to 180 milligrams per deciliter. So that's only one study. Let's look at data from another study. So in this study, they did a 24-hour infusion. And I should note that both of these data are in humans, not mice. So in this study, it was a 24-hour glucose infusion. And again, they raised basal levels of glucose from 95 milligrams per deciliter up to 192. So very elevated blood levels of glucose for a 24-hour period. So what was the effect on blood levels of CML? So we can see that data here, starting from a basal level of CML in blood of 74 nanomolar. After 2 hours, it wasn't significantly increased, but after 24 hours of continuous glucose infusion, we can see that CML levels were significantly increased when compared with the basal levels. So from these two studies, we can see that CML is significantly increased in the presence of high glucose. Now, note that 180 plus milligrams per deciliter is very high. It's nowhere near the age-related increase for blood glucose. So with that in mind, are age-related increases for blood glucose enough to increase blood levels of CML? Now, I didn't come across those studies, but if anyone out there has seen those studies, please post them in the comments so we can educate everybody about what happens with the age-related increase for blood glucose and its potential effect on blood CML. Now, blood glucose isn't the only factor that can increase blood levels of CML. Poor kidney function may also contribute. And note that poor kidney function declines during aging, which may be one reason for an increased level of CML in blood during aging. So here we can see the association for CML, again, N6-carboxymethyl-Lysine, with EGFR as an index of kidney function. So we can see that that association is inverse or negative, which means that the higher the blood levels of CML, the worse kidney function, as indicated there. Now, there weren't any pretty pictures in this study of people who had an average age of about 48 years. In a second, we'll look at people who were older. But in a simplified schematic of what that negative or inverse association would look like, I've plotted a standard negative association there with EGFR as kidney function on the y-axis against CML on the x-axis. So we can see with a negative or an inverse association, higher levels of CML would be associated with a worse EGFR or worse kidney function, and conversely, lower levels of CML would be associated with a higher EGFR or better kidney function. So that's what the negative or inverse association indicates. Now, in another study of older adults, in this case with a median age of 64 years, and again, we're looking at the association for serum levels of CML versus EGFR, we can again see this negative association. So in these two separate studies, we can see that the higher blood levels of CML were associated with worse kidney function. Now, hyperglycemia and poor kidney function or suboptimal kidney function aren't the only factors that can contribute to blood levels of CML. The gut microbiome may also contribute. So here in this study, mice were force-fed CML, and then CML in blood was quantified 4 hours later, which is what we're looking at on the y-axis, blood levels of CML, or the change in CML starting from baseline. And in this case, we're looking at data for young mice that were 1 to 2 months old, so very young, versus aged mice, 22 to 24 months old. And also notice there are two different shades for these bars. There's the light shading, which are SPFs, specific pathogen-free mice, so mice that have a defined microbiome, versus the purple bars, or the purple rectangles, which are germ-free mice, mice that don't have a microbiome. So in young mice, regardless if the mice had a microbiome or not, we can see that there are similar levels of CML in blood. However, during aging, we can see that aged microbiome-containing mice have increased levels of CML in blood, whereas the mice that don't have a microbiome did not have a significant increase during aging for CML. So where did the CML go in the mice that didn't have a microbiome? Remember, this is CML that's force-fed. Where did it go? So the ingested CML was not absorbed into the systemic circulation in mice that didn't have a microbiome, and we can see that here. So we're looking at CML content, and in this case it isn't blood, it's in the fecal pellet. So we're looking at data for the mice that have a microbiome on the left versus mice that did not have a microbiome on the right, and this is in the aged mice. And in the germ-free mice, the animals that did not have a microbiome, we can see a 4-fold higher content of CML in the poop when compared with the animals that had a microbiome. So again, the ingested CML in the microbiome absent mice was not absorbed. It was retained in the fecal pellet. So then the big question is why? So there's worse gut barrier function in aged microbiome-containing mice when compared with the germ-free mice, the mice that did not have a microbiome, and we can start to see that here. So here we're looking at relative permeability, and this is permeability of FITC dextran, so that's a fluorescent probe. So that is force-fed, and then it's absorbed, and how much of that is absorbed is reflective of how permeable the intestine is, or how good or bad gut barrier function is. So in young mice, we can see that relative permeability of the intestine is similar whether the mice have a microbiome or they don't. So, but then as the mice age, especially mice that have a microbiome, or more specifically mice that have a microbiome, have an age-related increase for worse gut barrier function or an increase in intestinal permeability as shown by that red arrow. However, for the mice that do not have a microbiome, we can see that there's no age-related increase for intestinal permeability. So the same gut barrier function in mice that don't have a gut microbiome. So with that in mind, interventions that improve gut barrier function should reduce absorption of CML into the blood. So that's what we're going to look at here. So relative permeability of the intestine. And in this case, mice were supplemented, the aged mice were supplemented with IAP. And IAP stands for intestinal alkaline phosphatase. It's a protein. And so what happened after IAP supplementation in the aged mice to intestinal permeability? So as we can see by that green arrow, it significantly improved. So IAP improves intestinal permeability. So then what happened to blood levels of CML in aged IAP supplemented mice? So we can see that here, blood levels of CML after the aged mice were force-fed. And in IAP supplemented mice, we can see that CML levels in blood were significantly reduced. So with that in mind, how can we increase IAP? That seems like it's a very important protein for reducing blood levels of CML. And I've covered IAP in an earlier video. If you're interested in that data, I'll leave a link in the right corner, so check it out. All right, to summarize, dietary age products impact lifespan in mice, and then dietary age products are not associated with an increased all-cause mortality risk in people, but there's only one study that exists. So if more studies are definitely needed to come to that conclusion as a more definitive conclusion. However, blood levels of CML definitely increase during aging, and blood CML levels are also associated with an increased all-cause mortality risk. Now, blood levels of CML are increased independent of the dietary story in the presence of high glucose, when kidney function is poor, and also when gut barrier function, intestinal permeability is high or gut barrier function is poor. So note that interventions, more specifically IAP, that improve gut barrier function lead to less blood levels of CML. All right, that's all for now. If you're interested in more about my attempts to biohack aging, check us out on Patreon. Thanks for watching. I hope that you enjoyed the video. Have a great day.